Hi class, I'm back for part 2 of chapter 13 lecture, and we'll start off with colligative properties. And colligative properties are the properties of a solution that depend on the amount of the solute, not the type of solute that's dissolved in the solvent. And the 4 properties that we'll talk about are VPL, vapor pressure lowering, BPE, boiling point elevation, FPD, freezing point depression, and osmotic pressure. So I'll go through an example of each of these with you and hope that it will help you understand what a colligative property is. So the first one, which is the vapor pressure lowering, what we know is that as a solute is added to a pure solvent, it becomes less volatile. And what volatile just means is the ability to evaporate. So it has less ability to evaporate. It has a decrease in vapor pressure. And so this is described by Raoult's law. And Raoult's law is the pressure of the solution, or the vapor pressure of the solution, is equal to the mole fraction times the normal vapor pressure at standard temperature, or whatever the temperature is that the scenario is taking place at. So in example 1, I have this, that glycerin is added to 500 milliliters of water, and the vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. So here we're defining the temperature at which I have a vapor pressure that's given, and I want to know what is the vapor pressure of this now solution. So what I have to do is I have to find, first of all, my mole fraction of my solute. I'm sorry, mole fraction of my my solute, that's what I meant to say. So if I have 50 milliliters of glycerin, which is my solute, that's added to my solvent water. So I know these parameters here, that the density is 1.26. So I can convert milliliters to grams, and then I can convert the grams to moles to find out the number of moles of my solute. I do the same thing with the water, knowing the assumed density of water is 1 gram per 1 milliliter, and I find out the number of moles of water that I have. So that's the first thing. Then what I do is I want to find what the vapor pressure is, what the new pressure is of the solution. So I take the mole fraction of my solvent, okay, which is the water, the mole fraction of the solvent, over the total number of moles. So I've just added the moles of the glycerin and the moles of the water to get my total moles. And then I use the vapor pressure of my pure solvent water. And so now I'll know what the vapor pressure of the solution is. So up here, where I have solute crossed out, that was an error, that should actually be the mole fraction of the solvent. So you want the mole fraction of the solvent if what you have for your original vapor pressure is for the water. Okay, things could change a little bit if your solute you were adding was a liquid. Then there'd be some adjustments that you would have to make in terms of finding your mole fraction. But in this scenario, since I'm given the vapor pressure of my solvent water, and that's what I plug in here for my pressure of my solvent, then what I have to use here is the mole fraction of the solvent. So if this is solvent, this is also solvent. And then this would give me the vapor pressure of the solution. Okay, so that's my first example. So then my second example, if I have the vapor pressure of water at 110 degrees to be 1070 torr, a solution of ethylene glycol and water has a vapor pressure equal to 1 atmosphere at this temperature. What's the mole fraction of ethylene glycol? So then what I do is I'm going to look at, okay, my same equation, which is the P equals X sub A times P naught sub A. So what I know is that the vapor pressure of pure water is given here. I'm going to convert that to ATMs because the vapor pressure of my solution is an ATM, so I have to be in the same units. So I'm going to take and plug into my equation for PA, which is 1 atmosphere, is equal to X sub A, which is going to be the mole fraction of my X sub A is the mole fraction that I'm given, and the value that I'm given for my pure solvent, which is water, is 1.41. Okay, so what I find here, so this is what brings me back to what I was trying to explain up here about whether or not you're finding the solvent or the solute when you're using this equation here. So what I'm finding now is the mole fraction of my solvent in this scenario, okay? Because I'm given the vapor pressure of the pure solvent, which is 1.41. Then I'm given the vapor pressure of the solution once the ethylene glycol is added. So the mole fraction that I get here is for my solvent, water. So then to answer the question, what is the mole fraction of the solute ethylene glycol? I have to take 1 and subtract 0.709 because that's the fraction, that's the water. If that's the water, then what part is the solute? So I would say 1 minus that fraction. Okay, so that should take us through vapor pressure lowering. Now to the second and the third colligative property, which is boiling point elevation and freezing point depression or freezing point lowering. So when solutes are added to a pure solvent, it causes the boiling point to increase and the freezing point to decrease. And the equations are pretty straightforward. So if it's a non-electrolyte, in other words, it's covalently bonded molecule that doesn't break up into ions when it dissolves in water, this is your equation. It's delta TB equals KB times little m, right? That little m there, that's molality, not molarity. Talked about those differences when we talked about concentration units. So this delta TB is the change in boiling point. The change in boiling point equals the molal boiling point constant for your solvent. So for water, it's this. Now, and so this is how I would calculate how much the boiling point increases, because remember, it's boiling point elevation. Now I'd use a similar formula to find out how much the freezing point lowers. Delta TF equals KF times, again, the molality of the solution. And the KF for water, again, this value here is given for whatever your pure solvent is. All right. And so for water, the KF value is 1.86 degrees Celsius per molal. Okay. So there's another equation you have to keep in mind, and that's if you have an electrolyte. So if I'm dissolving sugar in water, I would use this equation because it will dissolve as a whole molecule. It won't break up into ions. If I were dissolving sodium chloride, which is going to break up into 2 moles of ions, I would have to use this equation here, because what happens when I put salt in the solution is that it breaks up into Na ions and chloride ions. So I need to identify the number of moles of the electrolyte. And so here in this scenario that I just showed you with the NaCl, that value would be 2 moles of ions. So it's the same as above. Delta TB equals Kb, and the mole boiling point constant for water would still be 0.51 times the molality. But now I have to consider how much of an impact the electrolyte has on this. It's called the Van Hoff factor, and I is equal to the number of moles of ions. Okay, and then the same would be true for the delta TF. If you're adding an electrolyte, you would also include the I in that for the electrolyte. Okay, so then the last thing here is osmotic pressure. And osmotic pressure is the pressure required to stop osmosis. And osmosis allows for the net movement of solvent from areas of high solvent concentration to low, or low solute concentration to high solute concentration. And so what happens is that the solvent can flow through a semi-permeable membrane. And here I just give kind of a progressive diagram of what happens in terms of the flow across the semi-permeable membrane and how osmotic pressure is measured. And so there's an equation for osmotic pressure. The variable is the pi variable. And osmotic pressure is equal to MRT. And M is capital M for molarity, not molality now, as it was for the above equations, but it's now molarity, which is moles of solute per liters of solution, right? So that's from our concentration unit. It's mole per total liter of solution. That's an L, sorry about that. Okay, so pi equals MRT. And again, if it's an electrolyte, you would include the Van Hoff factor times the I. If it's sugar, you wouldn't include that. If it's sodium chloride, it would be 2. If it were something like calcium chloride, I imagine you could figure out what that would be. So how would that break up in a solution of water? It would break up into 1 positive 2 calcium ion, and it would break up into 2 moles of chloride ion. And so in this scenario, what I would have is an I value equal to 3. So those are just some examples of how I can vary. Okay, so since molarity is moles per liter, our equation can also look like this, which is osmotic pressure pi is equal to N over V, because N over V is really what molarity is, N representing moles times RT. And R is just that ideal gas constant from your gas laws chapter, which is 0.0821, and it's a complex unit. The unit is liter atmosphere per mole Kelvin. and it looks like that per mole Kelvin. And since that's the unit for this R, then it's important that you always use the Kelvin temperature here when you're doing this calculation. Okay, so I think this leaves you with an example here. So I could walk you through the example. I think it's pretty self-explanatory. You go through, you plug in the values that are given, you identify the Van 't Hoff factor, which is 3 because of the 1 here and the 2 here. You use your ideal gas constant. You use the Kelvin temperature, right? You have to be careful here. Make sure you're using Kelvin temperature. And then you would solve for your molality first. Then once you know the molality, you find out the volume, which is 50 milliliters, and then you can calculate your number of moles. Once you know your number of moles and you know your mass is 0.125, which is given in milligrams, you convert it to grams. Grams divided by moles will give you the molar mass. If we know the molar mass is 158, and we know that this metal, which we don't know what it is, plus 71, which is 2 times the value for chlorine, which is 35.5, then we can do a little calculation here to determine what the value of X would be. And then you're going to just do a little bit of algebra here and solve for X and find out that it's 87.23 grams per mole. And we find out that the metal that is my X value that I'm trying to identify is strontium. It's probably be worthwhile for you to kind of walk back through that example and let me know if you have any questions about it. So that's it. That's the end of chapter 13 lecture for now. And well, that's the end of chapter 13 lecture, but of course I can give you greater explanation on anything that you request. So we'll see you next time.